Hello and welcome back to the course on computer vision. And today we're talking about the multi-box concept behind the SSD algorithm. This is going to be quite a visual tutorial. So there we have Adlan standing on a pontoon at Lake Bohinj in Slovenia. And just as a side note, if you're ever in Slovenia or around there, definitely visit Lake Bohinj. It's a beautiful, magical place. As you can see, it's amazing there. There's also, those are the Alps behind. The view is really great. They have a lookout tower there, so you can actually go up and see all of the, like a huge part of the Alps from up there. Very lovely. We were there during our European road trip when we were visiting students all across Europe, and it was definitely a great stop. They have two big lakes in Slovenia, Lake Bled and Lake Bohinj, and this is Lake Bohinj. It's a bigger one. It's a bit further away from the main cities, but it is definitely worth the trip. And so, as you can see, we've already got a box around Adlan, identifying him as a person, that he's standing there, pointing. And what we're going to do today is we're going to take this box as the ground truth, and then we're going to see how the SSD algorithm works with its own boxes to actually identify Adlan and build this same exact box. And first things first, what is a ground truth? Well, a ground truth is a concept that's not just used in computer vision, it's used in many places, and it separates the observed evidence or empirical evidence from inferred evidence. So, for instance, when you go and actually look at something, and you see something and you can physically understand that this is the true state of things, that's your ground truth. There's no two ways about it. There's no gray areas. We can see exactly that this is the box that should be around Adlan. Whereas when you apply an algorithm and it processes all of this data through its convolutional neural networks and so on, and comes back with boxes, those are not going to be ground truth boxes. Those are going to be inferred boxes. Those are going to be suggestions brought up by algorithm. Even if they're correct, they're still merely suggestions. And in order to make sure that they're correct, we need to have the ground truth. And that's why in the process of training these networks, the SSD in particular, we need the ground truth. So we already need these boxes to be identified. We cannot just train the algorithm if these boxes are not present in the first place. That's something important to keep in mind for that training process. And yeah, so there is Adlan. Let's see how the SSD algorithm will work and build its boxes and how the training will happen. So what the SSD will do is will break down the image into segments, and then for every segment it will construct several boxes. It will construct a box like that, and a box like that. For instance, so these the exact setup can vary, but we're going to stick to this one. This is the most generic one. And basically the whole image will get covered with these boxes. As you can see, it's covered entirely. And then for every single one of these boxes, it's going to ask the question, is there an object in there or not? And not just an object. It's going to ask that question for every single class of objects that it's trained for, or in the training process is going to ask that question for every single class of objects that it is training for. And so basically in our case, it will identify that none of these boxes, except for the ones highlighted in red, actually have an object of interest in there. And we're going to assume that in this case, for simplicity's sake, that we're only looking for people. There are people in the background there, but they're very small, and the algorithm will not be able to pick up their features, and therefore will not detect those people. I will talk about size and scale further down in another tutorial in this section. For now, we're just going to focus on Adlan, and we can see that some of the boxes have picked up certain features of a human being in that part of the photo. So if we remove all of them, let's just look at one box, just so that it's clear why, for instance, this box is able to pick up that there is a person within this box, or so it doesn't have to be a full person. This is what I wanted to point out here. It doesn't have to be a full person or full object. As long as it can find a sufficient number of features, it will produce a probability. It will say that with a likelihood of 80% or 70% what I have in this box is a human being, or is a car, or is a boat, or is a cat or a dog. So in this case, it sees enough features to say that there is a human or a person inside this box. And yeah, then all of these ones that we have identified here can see the same, almost the same features. They're very different, a bit different features. But nevertheless, they all have enough, identified enough features, except for that green one. You can see that that green one, for instance, it only sees from the elbow downwards. So just for the sake of this tutorial, I decided to assume that it's not seeing enough features. Although, as you'll see from the practical side of things, that would be enough features for the SSD algorithm to detect a human being. But just for our case, I just wanted to show you that not always these three boxes, like you can see that the boxes come in threes in our case, that not always are they linked. So if one of them detects a person, that doesn't mean all of them detect person. So in this case, that one will be dropped. And so here we have not 6, but 5 boxes that have detected a person. And so that is the ideal case scenario, and that's what we're striving towards. That's what we want to train the network to do. And the way it will happen is, here's our network, and every time all of these boxes predict something, we'll have an output. So I'll bring the mouse here. So for instance, don't look at these small layers for now. We'll talk about them later. We're dealing with this layer over here. And so we've got all these boxes, and they all predict something. And so then the convolutional neural network searches for features. It predicts that, for instance, in these boxes that there's a human. That's what we want. But for example, if it had predicted that there's in these boxes is a human, or in these boxes is a human, and then on the other hand, it predicted that some of these boxes don't have a human, at the end we would have an error. How would we have this error? Because we actually have the ground truth. We have the ground truth with this white box, and we would actually know, by overlaying these images, the algorithm knows exactly which boxes should say yes, there's a human, and which boxes should say no. So it already knows. What we did actually here is, the red boxes are the ones that ideally should say there's a human, and we want them to say a human. And all other boxes, which we've deleted, should say there is no human, there is no person. And so, unless that is the case, there will be an error. So if, say, for instance, a box over here says that there's a human, and a box over here says that there is a human, and one or a couple of these boxes don't pick up the human, there'll be an error. And at the end of the algorithm, that error can be calculated. It can be expressed mathematically. We're not going to go into that. You can find more information on that in the annex on convolutional neural networks. But basically, that error can be expressed, and then what will happen with that error is it will be back propagated through the network. So it's just a visual representation, not necessarily into this spot, just back propagated through a network, and the weights of the network will be updated in order to better accommodate that, so that next time this box won't predict a human, and this box won't predict a human, but these boxes will predict a human. So it takes many iterations. It's going to happen on and on and on and on, but that's how the training process goes. And so the important thing here to remember is that we, unlike just simple convolutional neural networks, where we just want to predict if there's a dog on the image or if there's not a dog on the image, in this case, we actually need to find where on the image there is a person. And for that, we need a ground truth. So it's not sufficient for us to, for this image itself to be labeled that there is a person or there is not a person. No, that's not enough. We have to know exactly where the person is. So we need this box already on the image for the training process. And the way to think about it, kind of like the very intuitive way of thinking about it, is take each one of these boxes as a separate, think of each one of these boxes as a separate example of a convolutional neural network in practice. If you think of each one of these boxes as a separate image, that's what I mean. If you take each one of these boxes as a separate image, then yes, then that kind of is very similar to a convolutional neural networks, because for each one of the boxes, you just need to make sure it predicts that yes, there's a human inside this box, and you also need to know for the training purposes that indeed there was a human inside this box. So that's the ground truth in that case. So that's how it works. So like basically all of those boxes that we saw around, that were plotted around this image, you just can think of them as separate images in their own right, and each one is trying to understand, is there a human inside my image or is there not a human time image and doesn't care about the rest. But then the algorithm puts everything together on the end, and it takes the aggregate error, propagates it through the network, and trains everything up like that. So there we go. That's the multi-box concept of the SSD algorithm, and we will continue in the next tutorial. I look forward to seeing you there, and until then, enjoy computer vision.